Good morning, everyone. I hope you're enjoying the pleasant weather, warm, or at least pleasantly warm, not too hot, not too cold, and no rain. Normally, as we get closer to spring break, the weather gets a little rainy. So I was telling a student yesterday during a conference hour, I said, I hope we have some maybe more pleasant weather this spring break, but whatever, it's still a nice occasion to have days to rest and to rejuvenate, so to speak. Uh, Again, today we will continue our discussion on trigonometry. And of course, we'll have our second test at the end of the week, the same format as last time and the same window for testing on Thursday and Friday. I try to be consistent with the window of time, basically, so that you can get accustomed to that. And then, of course, I will always at least offer the same amount of flexibility and time as you have to navigate taking tests in other classes. So I would prefer to be on the positive side, giving you more flexibility than narrowing the time and making it difficult and increasing anxiety. That's certainly not what I want to do. So just remember, as I've said maybe 500 times already, this test will not include any trigonometry. It will end with the models in 4.6. So that'll give you an opportunity to see the introduction to the trigonometry, but not have to be tested on it right away. So what we want to do today, ladies and gentlemen, is continue with some of the properties of the two functions we've defined and then define the other four and just talk about, again, some basic characteristics of those, and then discuss the parent graphs of the sine and the cosine. Just like we do when we execute the transformations with logarithms and exponents, we've got the parent graphs and we can shift them around, we can compress them, we can stretch them. So we're going to continue to do the same thing with the trig function. So you'll have very, very good techniques that allow you to graph functions that don't require maybe more difficult techniques like calculus. When you get to calculus, there'll be some interesting functions that you will graph, but you'll always go back to these techniques for the more basic graphs just because they're quicker and they actually provide a relatively accurate graph. Now, of course, in calculus, you will learn the more fine aspects of the curve, like I've already talked about. But just like I say many times, when it comes to doing calculus, we take all the baggage from pre-calculus and college algebra and continue to use it. I'll keep reminding you of that, so at least you'll realize that what we're doing is important, and I want you to feel that way. Uh, when I worked yesterday with a student in conference hours in Calculus 2, we were doing just scads of trigonometry. And the comment was like, wow, I have to go back and review this. And even if you've learned it before, it still will get a little bit rusty. But that second and third time you see it, it's really easier. And so you really do learn it when you've got to use it to solve other problems. So let's go ahead and look at one of the most important properties of the sine and the cosine. And this is what I mentioned last time. And the nice thing about what we're going to learn about these functions is that since we're going to define the other four in terms of the sine and cosine, anything that we know about sine and cosine, basically, at least in terms of even and odd, can be transferred. So, what have we done so far? We focused on the arithmetic of the unit circle and reference numbers and how it impacts how we compute values of sine and cosine. So we want to move that into the four other trig functions. But first, I just want to say a little bit about why this is true. We've already developed a nice algebra, so to speak. Let me just adjust this a little bit so I can move my paper over. There we go. And shift this up a little bit. There we go. So basically what we want to be able to do is use the arithmetic we've already set up to verify these. And they're real simple to do. And it's going to help you as you navigate the arithmetic of the unit circle. So first off, number one, all we have to do is look in the four quadrants and verify this, because remember, modulo 2 pi, all we have to do is consider 0 to 2 pi. And then after that, everything's a repetition. And then, of course, if we move in the clockwise direction, we generate the negative real numbers. So the idea is that we don't have to exhaust the real line every time we do a proof. We just can focus on the unit circle. So first, we'll use the same letters we used before. We'll say T is in the first quadrant, and it will correspond to a terminal point, XY. Now, of course, last time when I was using a different T, it wasn't necessarily the additive inverse of this when I was describing the motion on the unit circle. Now we are going to look at the additive inverse because that's the basic premise of the even and odd. Now, first, let me just also note that we know that the domain of cosine T, and which also equals the domain of sine T, is all real numbers by definition. So we don't have to worry about lack of symmetry. We have a nice symmetric interval, so to speak, infinite interval about the origin. So that part we get for free. That's always the first thing we have to check with even and odd. So that I don't want to overlook that like it's unimportant. Of course, it's very important. And so now if we have T in the first quadrant, this will imply that the negative T going in the opposite direction will be in the fourth quadrant. So we've already used this argument before when we were talking about the values of on the unit circle as far as their terminal points. Remember, we did pi over 6, we did pi over 4, and got pi over 3 for free. So these types of arguments, again, they're going to come up over and over again. So by the time we finish this, you'll be really, really good at this. So now, if we move into the fourth quadrant, notice the x stays the same, but the y becomes negative. Again, because we're moving into the fourth quadrant, just using the symmetry of the unit circle. So now we can just say, all right, well, we'll start with cosine. Cosine of the additive inverse of T will now be X, because remember, cosine is the X coordinate of the terminal point, but that's also cosine of T. So that works there in the first quadrant. That is, the cosine function by definition is even. And sine of the additive inverse of T will be negative y. But that equals, again, the negative of sine of T by definition. So now we see that the sine function, at least in the first quadrant, is odd because of the negative factors. So the arithmetic we've already established makes these proofs very straightforward. But without that arithmetic and the convention of moving counterclockwise to give plus and moving clockwise to give negative reals, we couldn't do any of this. So when students complain about not starting with triangles, I tell them, you will never understand the arithmetic of trigonometry unless you know the unit circle. So one of the genius aspects of Dr. Stewart's book is that he starts with this. I've read many books on trigonometry and looked for many books when thinking about something for this class. And the Stewart book, albeit not perfect, no book is perfect. I mean, please, we're lucky to find a decent book, but the structure is very good because it paves the way to understanding. Again, in calculus, the arithmetic of the unit circle is imperative. Without it, You can't do polar coordinates. You'll make tons of mistakes in your integration techniques. So this is very important. So the reason I focus on these aspects is not because I'm trying to make your life miserable. I know what you have to do in calculus, and I know what students struggle with. So if you pay attention to this, you can hopefully enjoy calculus. So now let's look at the second quadrant. Now, after you do this, you can teach this to one of your friends, and then they'll say, "Well, I don't care about this." Well, they do care. Okay, so now we'll do the same setup. T will be in the second quadrant, and that'll just correspond to the point X, Y. That's just our arbitrary point. Now, this implies the additive inverse of T. Again, we're going to wrap around in the clockwise direction, and that's going to put us in the third quadrant, right there. So now, again, we have a point X, Y in the second quadrant. Now, when we look to the third quadrant, again, let me just draw this so you can believe me. This is what I'm doing, but sometimes just a little visual is good. So remember, right now we're thinking of distance along the unit circle. So if we terminate here, we just call this T. This is the second quadrant, and we terminate at the point XY. Right there. And now, when we do the additive inverse by symmetry, we're right here. So this arithmetic we've already developed is very nice. Now, of course, now this terminal point will obviously be what? X negative Y, because now we shift down. So now we can say, okay, this corresponds to X negative Y. So that's what I've been doing. You don't have to draw this, but it does help to maybe give a visual, even though that's really not the proof. We draw pictures, ladies and gentlemen, to organize our thoughts, but that's not a proof of anything. A picture is never a proof. Unfortunately, you've been taught that, but I've got to unteach it because it's not valid. We draw pictures to organize our thoughts, and that is good. Like we do charts when we do time, rate, distance, we do blanks when we do fraction of work or whatever. Most of you don't follow my ideas with that, and that's why you always miss the problems, or you just copy some solution from an internet site, which I saw on the first test. Let me just also mention this. In the future, if I start to see more solutions that look like an internet site, that's going to be a problem. So if you are using homework internet sites, stop. Come to me, ask questions. That's how we work in my class. And that's how we work at Sanjak. The next time you're on Blackboard, I want you to read the academic philosophy of San Jacinto College. It is very strict, and I abide by it. Okay, let's look at number 3. Now, of course, we can go ahead and do this. Before we do that, we have cosine of the additive inverse of t will now be x. We take the x coordinate, but of course, that's just cosine of t. So this works. Now you see the drift of this. And sine of the additive inverse of t is negative y, but of course, that's just the negative of the sine of t. So we're basically getting this for free. And now for 3 and 4, let's just go ahead and finish it off so you'll have a complete proof. And I probably will test you on this since I'm bothering to do it. So we have t, okay, now we've done the first 2, let's do the third quadrant. And that'll just correspond to a terminal point xy. You can use any letters you like, but x and y are useful. So now, again, as we move around to the third quadrant, and you can go ahead and put 3 in here, we'll just use this picture. Then if we do the negative, that'll actually end up in the opposite, that is in the second quadrant. So now this implies the additive inverse of t lives in the second quadrant. And so now, again, we're going to move up again. The x won't change, but the y will become its additive inverse because you're shifting up into the other quadrant. So now cosine of the additive inverse of t is x, which is also cosine of t by definition. And sine of negative t is negative y, or the additive inverse of y, which is the negative of sine t. So again, so far so good. We have one more quadrant. And again, this, excuse me, this technique and this structure that we use, again, I've written many proofs on even and odd, but this is one of my favorites because it's the most straightforward and it's the simplest to remember. And of course, it's all based on how we've designed the unit circle and its structure. So now the very last one is, let's just start in the fourth quadrant. And we have a terminal point of xy, arbitrary point. Now, again, if we're thinking over here in the fourth quadrant, as we go negative, we move into the first quadrant for the negative, just like we had before. So the additive inverse of t. So it's basically the flip of what we have here. It's that they're symmetric. And we have the same thing again. We're going to shift up. So the x always stays the same, but the y always shifts. So now you can see how the even and the odd just fall out very simply. So now we have cosine of the additive inverse of t is just x, but that by definition is just cosine of t. And then, of course, sine of the additive inverse of t is negative y, but that's just the negative of the sine of t. So I wasn't kidding when I said that the arithmetic of the unit circle is really the crux of what we do. We love triangles to solve problems, but we always have to move a little bit away from the triangles to make sure that we get our signs correct. Okay, triangles are a great convenience, and without them, we would struggle to solve a lot of problems in engineering, physics, and mathematics. So now we can see at this point that I've got my railroad tracks here. There's a complete proof. This covers the entire unit circle, all four quadrants. And since we can always reduce any input via reference number to this, that is, we get rid of all the multiples of 2 pi, and we find ourselves in the positive realm 0 to 2 pi. So that's all we have to worry about. And then, of course, if we're computing things, we can always use the reference number. Again, there's so many arithmetic ideas available to us that we just can pick and choose sometimes. Now I want to make a few comments here. If we know sine and cosine pretty well, we can see that if we define the other four trig functions in terms of these, the even and the odd qualities will pass to them. So let's go ahead and do that. Now, here's our next definition, and I'll call this, let me just call this Roman numeral 3. This is going to be the tangent function. Now, we have a special abbreviation for this. For instance, for cosine, we do cos, and then for sine t, we just do sin, sin t, just because we're lazy, but again, it's convention. So we say tangent, we just do tan of t. And of course, when I do this, ladies and gentlemen, I'm not always being sloppy when I don't put parentheses here. WebAssign will do it. But again, if we don't do it, it's because it's clear that we're taking the argument or the tangent of t, that t is the argument. But of course, if we have sums and things like that, we really do need the parentheses. There'll just be times when we get lazy, but it's a common notation. So I want you to get used to it. Now, just on the after I define this, I'm going to go back to the definition of the unit circle to give you the fundamental identity, because you might have already forgotten it. So we're going to define sine t to be, excuse me, tangent t to be the ratio of sine t to cosine t. Okay? So we're thinking, when we look at this, we've taken two functions that we understand pretty well and we take their ratio. Now, of course, the tangent function will have obviously vertical asymptotes because there will be zeros of cosine that are not zeros of sine. So this will not be defined for all real numbers, but via the vertical asymptotes, and we'll say more about this later, the function will tend to unbounded nature positively and negatively. And so the range will actually be all real numbers, but we have to think a little bit about the domain. So again, let's just go ahead and write it. The domain, in this case, I'll just write out the word, the domain will be all t, such that in this particular case, t does not equal, that is, we don't need pi over 2 because that makes cosine 0, but anything pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, negative pi over 2, negative 3 pi over 2, all of those numbers create zeros for cosine. So we can just say pi over 2, and we'll make this look a little bit neater, plus integer multiples of pi. Now, the book sometimes will use a K, sometimes they'll use an N. Here, they're using an N, so we're going to say N is an integer. Okay, so basically, if we look at this, we can dress it up a little bit and just say, for instance, so we have t not equal to pi over 2. Let's put in two 2's here. So we'll have 2 pi n over 2. Let's just dress this up so they have the same denominator. It looks like a lot of overkill. But now when we factor the common factor, which is pi over 2, we'll get a 2 times an n from this term and a 1 from this one. So this might be an easier way to remember the domain. Now we can say that we must exclude odd multiples of pi over 2. So 2n plus 1, where n is an integer, gives us 3, 5, things like that, 1, negative 1. Usually when we think of odd, we just think of the positive numbers that aren't divisible by 2. Of course, we can go into the negative realm. And so now students often like this when they just say, well, we got to kick out the odd multiples of pi over 2. So this might be a better way to think about the domain of the tangent function. Okay. Now, as I said before, the range will be all reals because of the vertical asymptotes. And we'll say more about that when we talk about the parent function of tangent. So for now, we want to go ahead and write this down and keep it in our back pocket. So one thing that's very interesting, and we'll see more of this when we talk about the graph, is that because of these vertical asymptotes, we can have a principal branch from negative pi over 2 to pi over 2, which covers all real numbers. But due to the unit circle symmetry, that principal branch will repeat over and over. So what we're noticing, at least by definition, is that cosine and sine have a basic period of 2 pi. The unit circle is modulo 2 pi, but the tangent function has a smaller basic period, which is pi. So let me just reiterate, cosine of t, and we'll just use t for now since we're using that. Later on, we'll use x and not worry about it. We'll have plus multiples of 2 pi, integer multiples. This is always going to be cosine t. So we'll say n is an integer. So we're going to say cosine is 2 pi periodic. The same is true for sine. We're just wrapping around the unit circle. This would be true of any trig function, but what we're going to find for tangent and cotangent is that they actually have a smaller period due to the symmetry of the unit circle. So 2 pi n is sine t. So we say 2 pi periodic. When we talk about a period of a function, we're thinking about the smallest positive real number that does not change the input. So we just say, if we just take all the n's away, we just say cosine of t plus 2 pi equals cosine of t. And 2 pi is the smallest positive real number that accomplishes this. And then, of course, if you add any multiple of 2 pi, you're just wrapping around the unit circle and accomplishing nothing. You end up at the same point. So this focuses on the fact that they are indeed 2 pi periodic. These are important concepts. They seem really simple, but we say 2 pi periodic. Now, the tangent function is one better. It is pi periodic. And certainly 2 pi is a multiple of pi, so we get the same thing. But now we can say tangent t plus multiples of pi will still be tangent t. So we can do it one better, pi periodic. So when we think about these functions, modulo 2 pi is how we operate on the unit circle. And that basically gives us the basic period for sine and cosine. But the way we define the tangent function, we do one better. We actually shrink the basic period to pi. So that's even better. There's always a nice test question where you say, you say tangent of t equals, say, 1/2. And then for instance, here's a nice example that we'll say tangent of t equals 1/2. And then there'll be a problem that says, well, what is tangent of t plus tangent of t plus 10 pi plus tangent of t minus 20 pi? I mean, obviously, this is a simple question. Well, these are all multiples of pi, so they do not change the value. These all equal 1/2. By this identity here, this is 1/2 because 10 pi is just a multiple of pi, so it doesn't change the output. So we'd say this just equals 1/2 plus 1/2 plus 1/2, which is 3/2. So there are nice properties about the tangent or the trig functions that make computations very simple. And if you ignore them, you might stare at this problem and just make something up. So remember, this periodic nature of these functions really helps us out when we graph a function. All we need is to graph an interval of a period length for that function, because after that, it will simply replicate. We just get repetitions of the same graph. That's what we mean by periodic function. And ladies and gentlemen, we haven't spent much time with periodic functions, basically none. So the trig functions are really, really unique in that aspect. And that's why Fourier, or that's what Fourier did. He exploited the periodic nature of the trig functions to create his method of analysis called Fourier analysis. So all of you future electrical engineers, you have to say your hats off to Fourier for paving the way for our understanding, of electricity, and that pushed forward what Tesla did, and just made us smarter and happier as human beings to have electricity. So the idea here is this new function has a smaller basic period. Now, let's just go ahead. I mean, and then of course, evaluating it, we'll just be evaluating it in terms of sine and cosine. We'll do several of those, but let's just go ahead and prove that tangent is odd. Okay, so now we say the domain of tangent t will be all t such that t does not equal odd multiples of pi. And that gives a nice symmetric interval. That is, we take out all the odd multiples of pi. So pi over 2, negative pi over 2. Okay? 3 pi over 2, negative 3 pi over 2. Those are all symmetric about the origin. So this is a symmetric domain. Symmetric about 0. Remember, we need that. If t is in the domain, its additive inverse must be in the domain, because that is the first premise of the definition of even or odd. So we get that for free, all right? Again, we don't need to ignore it. Sometimes we don't even think about it because we're so focused on the second part. But ladies and gentlemen, if you don't have this symmetry about 0 in the domain, even and odd makes no sense. So now we're thinking, okay, well, let's just take t in the domain. So now we'll be formal, but this will be so much easier because what we've done. Let t be in the domain of tangent. Then tangent of the additive inverse of t, we'll use our parentheses now because it helps in clarity. This will be sine of the additive inverse of t divided by cosine of the additive inverse of t by definition. So students always say, I just have to go back to sine and cosine because those are the building blocks, so to speak. And so you will navigate trigonometry based on how it makes sense to you. I will give you all the details and all the strategies, and you'll have to come up with the best way to assimilate them so it makes sense, and it will make sense. So now, of course, sine is odd, so the negative factors. Cosine is even, so the negative absorbs. And so this is just the negative of what? Sine of t over cosine of t, but that's just the definition of tangent. So this is the additive inverse of tangent of t. So we get the fact that the tangent is odd for free. Okay, so tangent is, when I say tangent, the function tangent is odd. Okay? So again, this property is important because, like I said before, if we have negatives or additive inverses in the argument, we can either remove them or factor them. And that makes our arithmetic easier. So again, I mean, you know, we'll take what we can get, ladies and gentlemen. If you don't use the mathematics, then you have to work harder. Everybody always says, oh, Professor Ron, thanks for the shortcuts. No, they're not shortcuts. They are simply good mathematics. If you can always do the problem the long way, and what I find with a lot of you, you look for the shortest possible execution. And so that's the idea. What you might think is a shortcut is just simply utilizing good mathematics. But as long as the mathematics is acceptable, I don't really care how you do it, but I do want you to finish the problem. So now let's go ahead and do Roman numeral 4 here. Now, I wanted to remind you of some notation that's important to us, and we'll use this later on. Remember, we know that x squared plus y squared equals 1. And of course, these are terminal points on the unit circle, and we know x corresponds to cosine and y corresponds to sine. So we can say cosine t, I won't use the parentheses here because it gets a little bit in the way, squared plus sine t squared will now be 1. And this is what we call a term, the fundamental identity. This is true for all real numbers. So any value of t that you input, this is valid. So anytime you see cosine squared plus sine squared, that's 1. That's fundamental. Now, it is convention. We use this for trig functions. I do not use this for logarithmic functions, even though I have colleagues that do, not a problem, but it's not very standard. We don't mind writing it this way, but it is a standard notation to put the square before the argument. So we read this as cosine t quantity squared. Now I'll be lazy at times. I'll just call this cosine squared. Remember, this has nothing to do with squaring the argument. It just means cosine t quantity squared. And this shorthand is universal. It is used everywhere. And I will use it and you will use it to save sanity. So this will be what we will adopt. And if we had a cube, cosine of t quantity cubed, we could put a 3 there. So we'll do the same for the sine function. This is what we call one of the Pythagorean identities because it's basically, well, it's based upon the Pythagorean theorem. You probably thought about that. We say Pythagorean identity. So it's important. And we're going to write other Pythagorean identities as we define the other three trig functions, and we'll put them together and keep that list because, again, those will be important identities and formulations. So basically, ladies and gentlemen, our entire study of trigonometry and our identities will all pretty much flow from this single identity here. And it's kind of amazing that we get all this output from what seems to be very simple and maybe not that important, but it is. So now we have cotangent. Cotangent. I didn't come up with these names, but they have to do with function and cofunction. So we now know that tangent and cotangent will be cofunctions once I tell you what that means. And sine and cosine, they must be cofunctions too. So that'll be something we'll do later. And we'll say this is the cotangent function. That's the formal name. And of course, we'll be lazy and say COT, cotangent T, and I'll use the parentheses here so the T's don't run into each other, cotangent T. And this is actually going to be the reciprocal of the tangent. You're thinking, why do we need this? Well, it has proven to be very useful. The calculus is useful. So you might be wondering, were these surmised in a short period of time? No, over time they developed, okay? And the 6 trig functions that we define are basic and fundamental, and they seem to be the most useful in doing the mathematics that we need. And then, of course, we're going to talk about inverse trig functions. So if the list is not too long, we can survive. But now you can see by definition, this is just the reciprocal of tangent of t. Okay, so there's an identity right there. The cotangent is the reciprocal of the tangent function. So it's just cosine over sine. A lot of times we'll just say tangent, sine over cosine, cotangent, cosine over sine. Now, of course, by the same argument, the cotangent will also have vertical asymptotes, and in its fundamental branch, it will cover all real numbers like the tangent, okay? So we can already rest on the fact that the range of the cotangent function will be all real numbers. I'll just write it this way. The range will be like the tangent. It'll have principal branches. But now with the domain, we're going to look for all real numbers t. And of course, we don't want the sign to be 0. And we know that the sign is 0 on the x-axis. That's where the y values are 0. So we say this is much easier. T not equal to integer multiples of pi. So we don't have to do any interesting algebra here. We just want to avoid integer multiples of pi. So again, we'll say 0 pi, pi, 2 pi, 3 pi. That's when we're right, when we do our measurements of t, we terminate on the x-axis outside of the quadrants, so like on the boundaries of the quadrant. So you might say, if you're right here, which quadrant are you in? Well, you could claim 1 or 4. It won't matter. It won't change the arithmetic. So the idea is if we divide by 0, that will define, or if we try to, that defines the vertical asymptote. Of course, we know that's undefined. So now we're thinking, okay, does this do the same? Absolutely. The principal branch will run from 0 to pi, like the principal branch of tangent runs from -pi/2 to pi/2, and that length is pi. So again, we get the same pi periodic. That is, cotangent is pi periodic. And so, of course, cotangent of t plus multiples of pi, where n is an integer. Again, n is always an integer, at least in our discussion today. We just get cotangent of t. This is very important, ladies and gentlemen, and it's what I've been doing from the very beginning when you mod out by 2 pi. So when you think about cotangent and tangent, you're like, okay, you know, you add a multiple of pi, you might as well just get rid of it. It's one better. It's one better. It's not, it's better than doing modulo 2 pi on the unit circle. So you can just think of the n pi as a 0, just like we did with the tangent function. It won't have any impact. So again, none of this would make any sense if we weren't thinking about the unit circle. And so a lot of students will say, okay, well, if I know my cosine and sine, you know, I can use my reference numbers and figure out what these are, take the ratio and get that. Or if we've gone ahead and computed tangent, we get cotangent by just reciprocating it without having to go through this definition. So you will find yourself using this if you're starting with this, or using this if you've already computed the value of tangent. Okay, so that's all we need to say about that one for now. Now the next function is the secant function. Secant function. Now again, you know, these names, you might be thinking, who came up with these names? They're so interesting. And again, if you all ever get bored one day, just check out some math history and see, you know, where these names were devised, because I don't know as much math history as I should know. But if you're just interested over break, check into that. That might be very interesting.
Professor Ron?
Yes.
Sorry to interrupt. I've just got this question. So when we talk about fundamental, I know that it's supposed to mean like, well, it's important, but does it mean that like it's the foundation of that whole theory? Or like, what does fundamental really mean in mathematics?
Well, fundamental, it's like when I say cosine squared plus sine squared equals 1, that's a fundamental identity because it ties everything together. It's kind of like when we say algebra is fundamental to trig, it just means if you can't do, fundamental to calculus, if you can't do algebra, then you can't do calculus. That's what I mean by fundamental. Fundamental has a broad umbrella.
Oh, okay. So when they say, like, for example, the fundamental theorem of I don't know, algebra or calculus, so it just means that it's calculus needs it to work well, I guess.
Well, absolutely. It's a unifying theorem. That is, it touches all aspects of calculus, just like the fundamental theorem of algebra says that any complex polynomial of degree 1 or greater has at least one complex 0 is fundamental. That is, it stretches throughout the entire study. So when you say fundamental theorem of calculus, that ties the concept of differentiation to integration. So absolutely. And that is just a definition of the word. Absolutely. Yeah.
Oh, that's nice. Thank you so much. Yes.
Well, thank you. And maybe you must be really good in English because you're really sticking to those terms. So good for you. Thanks for that question. Now, the secant function, again, what do you might think that is? I mean, what could we reciprocate that we haven't reciprocated so far? Anybody? What have we not reciprocated? Well, Professor Ryan, I know we haven't reciprocated cosine, so that's going to be secant. So we say secant of t will be 1 over cosine. And again, these have turned out to be very, very useful, okay? So you might be thinking other trig functions may have been proposed, but they kind of fell out in the wash because they didn't really go anywhere. These have turned out to be very useful. And now when you think about this, if we look at this one and say, okay, let's go back, we already know what the domain is because we don't want to divide by 0. It's going to be the same as the tangent function. So we've already done the work. So we can't divide by 0. So this implies that the domain will be all real numbers t such that t does not equal odd multiples of pi over 2. Again, n is an integer. So we've already done that work. So we got that for free. Now, the secant function is very interesting. We know the maximum of cosine is 1, the minimum is -1. And so when you reciprocate numbers between -1 and 1, they go beyond that. They go beyond that interval. 1 stays 1, -1 stays -1, but 1/2 becomes 2. 2/5 becomes 5/2. So all of the numbers in the open interval move outside. So just by definition, this implies, and this is so simple, that the range will be a disconnected set. That is, the range will go from -infinity to -1, and then we have this gap to 1. So this is by virtue of the fact that we are reciprocating numbers between -1 and 1. The 1 and -1 are fixed, but all the numbers in between move outside, as I've just said. So this really does make for an interesting parent function. Again, when you reciprocate a function, you can kind of stare at the cosine function and visually reciprocate it. And that is really a good way to get the parent function. And we'll say more about that. Now, I want to say up here, just like this, and I'll go ahead and add this in, like tangent, cotangent. What? So tell me something. What is cotangent? Is it odd or even? What's cotangent? Someone tell me that. Is it odd or even? Don't be afraid. I'm not going to yell at you. Well, maybe I'll try not to. What's cotangent? Is it odd or even? Well, everybody's so nervous. Okay, well, look, tangent was sine over cosine. So if we flip this, we're going to get the same arithmetic and end up with the negative of cotangent. So cotangent is also odd, right? It's also odd by the same argument. So now look at this. Sine is odd. Tangent is odd. Cotangent is odd. So that's 3. And now when we look, and okay, we can go ahead and do another proof. So I want you to, mimic this proof for cotangent to get this. And now secant, we're thinking, all right, secant is possibly even since cosine is even. Again, we have a nice symmetric domain. So let's do the same thing. Let's just check it out. And again, if we want here, secant, like cosine, 2 pi periodic. And we'll say secant of the negative of t will now be 1 over cosine of the negative of t by definition, but cosine is what? Even. The negative absorbs. but that's just the definition of secant. So what we see is that just like the cosine function, the secant function by definition is even. So this implies secant is even. Okay? So we we do a little bit and we just spread it out. We just spread it out. You know, it's like we keep saying the same thing over and over, but we've been doing that from day one, right? Every time we solve an equation, zero product, right? Factoring, zero product. I mean, it's our bread and butter if we want to do solve equations. And any mathematics you do, you will eventually have to solve some equations. So now we're thinking, all right, we've got 6 of these. So for right now, secant is even, cosine is even, and we think we've got to do one more function, which is to reciprocate the sine. We reciprocate the cosine, and that'll be the last one. We're going to call that the cosecant. And so, of course, the secant and the cosecant will be cofunctions when we define those. So just keep that in your brain. So 6, we'll call this the cosecant function. Cosecant. And of course, we'll be lazy. This is a little bit harder to write. It'll be CSC. Now that's not very user-friendly. Secant, a little bit easier. Tan, cotangent. Cosecant's a little less user-friendly. So we use CSC of tangent, excuse me, of t. And this will be 1 over sine t. So these are reciprocals. And so again, we're thinking, all right, well, we don't want to divide by 0. So we've already done this work. This implies that the domain will be all t such that t does not equal multiples of pi. We don't want to divide by 0. Again, n is an integer, okay? So just like sine, cosecant is 2 pi periodic. We don't get any improvement there. We'll see that when we talk about the parent graph. And then, of course, just like before, the sine function is bounded between -1 and 1. And as we start reciprocating, we do the same thing. The numbers between -1 and 1 move outside of the interval. So again, we have the range, just like the secant function, will be -infinity to -1. Then we have the gap to 1, infinity. So the idea about the trig functions is that we have our base trig functions. We have the unit circle, and we define 2 functions based upon the terminal points on the unit circle, where the input is an abstraction. Think about it. The input is a measurement of distance on the unit circle. That's the input. We have never done anything like that before. But the beauty of it is we identify the unit circle with the real line. And then it starts to make sense. And the pi is boom in our face because it is the actual length, the curved length of the unit circle. So again, we started our discussion with Euclid, basically. The ratio of circumference to diameter of any Euclidean circle is pi, just like we had E with the natural exponential. Pi is just as important. So again, you know, we don't want to overlook all of the other transcendental numbers that are out there. We just haven't found maybe too many good uses for them, okay? So when we look at this and we think about these functions, we can now compute some more values. But what I want to do, and do a little bit of algebra, what I want to do is just go back to these identities. And what did I call them? I call them fundamental. So remember, the first one cosine squared t plus sine squared. So usually I'll just say, I won't usually say cosine of t quantity squared. I'll just say cosine squared sine squared. That is cosine of t squared sine of t squared. So to shorten that, we'll just usually say cosine squared sine squared. Any input will still give us a 1. 1. And this is what we call the fundamental, using that word again, fundamental identity of trigonometry. And this, again, what's an identity? An identity is an equation that is valid for all values of the variables for which it is defined. An equation that is valid, an equation that is true for all values of the variables for which it is defined. We did those with the exponential rules. We did those with the logarithm identities, as long as it's defined. But this is defined for all real numbers, so we can say t is a real number. Now we can do two more Pythagorean identities by just a little bit of algebraic manipulation. However, it won't be that all real numbers will work, because we will have some division by 0, but that's okay. We will still have very, very useful identities. The second one looks like this. We take this equation and we divide by cosine squared. So cosine squared t, of course, we don't want t to be an odd multiple of 2 pi or pi over 2, obviously. And then we have sine squared divided by cosine squared, and then 1 divided by cosine squared. Now what we can do is just use our laws of exponents. This is just 1, so we have 1. And then this is just sine t over cosine t squared. And this is just 1 over cosine t. Again, being a less formal with the arguments without the parentheses squared. But now we just know that sine over cosine is tangent, so we get tangent squared, and 1 over cosine is secant, so we get secant squared. So equivalently, 1, do a little lamppost, 1 plus tangent squared t equals secant squared t. So fundamental, and then you're thinking, okay, so we just manipulated this and we have a new version of the fundamental identity. There's another version of it. But we don't usually say, oh, well, this is the second version. We just say, well, that's a Pythagorean identity, and we find it to be very useful because it associates tangent and secant in a very useful way. Okay? Like this associates the sine and the cosine in a very useful way. Okay? So again, why do we write this down? It has served to be very useful. It has actually made a place in trigonometry because of its utility. So you think you could probably come up with all kinds of trig identities when we get to identities formally, and we prove some of them. It's like, well, why don't we put this on the list? Well, the ones that will end up on a basic list will just be those that occur most often. If you go on into Fourier analysis, there'll be some other identities that we learn in this class that you will actually learn or use more in Fourier analysis. And then, of course, you'll commit them all to memory because you use them all the time. So just because, you know, an identity doesn't make a basic list doesn't mean that it's just not worth our time. It's just that maybe it doesn't occur as often in the type of work that we'll be doing in calculus. Now, the third one, let's just take this equation and divide by sine squared. So cosine squared t sine squared. Of course, now we don't want t to be a multiple of pi because we don't want to divide by 0. So that's clear. Sine squared t, sine squared t, and then 1 divided by sine squared. You think, well, we're just doing the same thing. And again, you can divide by other terms. But again, what we want to generate in each of these is a Pythagorean equation that connects sine and cosine, a Pythagorean equation that connects secant and tangent. And of course, in this one, you know, we're going to connect what? We're going to connect what? Cosecant and cotangent, just like we did in equation 2 for secant and tangent. So now, of course, this we can write as cosine t over sine t squared. Now, of course, this is just 1, and this will be 1 over sine t quantity squared. So now, of course, it's convention just to write the 1 first. And of course, cosine over sine is cotangent. So we'll say cotangent squared of t. So cotangent of t quantity squared using our shorthand notation. And 1 over sine is cosecant. So this will be cosecant squared of t. And again, these are what we call the 3 Pythagorean identities. So we call these the Pythagorean identities. And they are true for all values of the variables for which they are defined. And of course, here we have t is not equal to odd multiples of pi over 2, and here t is not equal to n pi. These are so useful that you'll find that out as we work through the class. When you get to calculus 2, even in calculus 1, they're useful, but when you get to calculus 2 and techniques of integration, especially trig integrals and trigonometric substitution, these will be indispensable. So there'll be uses of this. Trust me, there'll be plenty of uses of this. Now, what we want to do is computing values fairly simple. I mean, we know how to do the arithmetic from our last lecture, but I want to do some algebra with these newfound ideas here. So let's do some algebra. So the very first one, and this is what I like about Dr. Stewart's textbook. Here's an example where we can use these Pythagorean identities. So in this case, we have right, and this we'll do an easy one. Right, easy, start out with easy. Write secant t in terms of tangent t. Okay, and of course, due to the arithmetic of the unit circle, we really do need to know where t terminates because we would have the choice of plus or minus. So we're going to say t terminates in the third quadrant. Okay, so again, when we think about that, we think of the third quadrant. We know the x is negative. So this implies that secant t, which is the reciprocal of the cosine, which is negative, is less than 0. Again, if t is in the third quadrant, then we know that the value of x, that is, which defines of the terminal point, which defines cosine, we know it's less than 0. And of course, its reciprocal would be less than 0. So now we're good to go. So whatever expression we have for secant, it should reflect the fact that its value is less than 0. Okay, that's important. So now we know from our Pythagorean identities that 1 plus tangent squared t equals secant squared. So we're thinking, okay, well, now we've got the what? What's that theorem that we use all the time? The square root property. We have secant squared is 1 plus tangent squared. So we're thinking square root property. So this implies that secant t is now plus or minus the square root of 1 plus tangent squared. But now we use our hypothesis that t terminates in the third quadrant, so that means we select negative radical. So this implies that secant of t will now be the negative of the square root of 1 plus tangent squared t. So the idea here now we see that this part here is positive and the negative makes this less than 0. So this is a verifiable expression of secant t in terms of tangent t. So what's important here is that if we're not given information about where t terminates, this is the best we can do, okay? Because if we are in quadrants 1 and 4, where cosine is positive, then we would have no negative. So if we don't have this information, that is every time we solve a problem in trigonometry, we have to know where the t lives. We have to know certain information so that we can actually determine the arithmetic, determine the plus or the minus. So again, you can see, even though right now this seems to be very academic, and it is, when you get to calculus, this type of technique will be indispensable. It will be something that we depend upon. Now, let's try another one, and then we'll compute some values. The next example says, write, in this case, cosecant t in terms of cosine of t. And in this case, again, not to beat a dead horse, t terminates in the third quadrant. You can make these up. You can just make up these problems and test yourself once you finish your WebAssign. So now we're thinking, okay, well, we know that cosecant is 1 over sine, and then of course we have the Pythagorean identity that establishes the connection between sine and cosine. So first, before we even do that, notice t is in the third quadrant. So this implies that sine of t, I'll just even write more this time, sine of t is less than 0. That is, the y value is negative in the third quadrant, which equivalently, hard to say, cosecant of t must be less than 0. So whatever expression we have, it must validate the fact that the value of cosecant t will be less than 0, will be negative, okay? So now we're thinking, all right, well, let's do it. Cosecant of t is 1 divided by sine t. Now, when you think about this and you think about what we need to do, we need to make sure that we have a negative. This is fine, but we want to write in terms of cosine t. So here's the next step. We'll go ahead and just write the absolute value of sine t with the square root of the square, and then affix the negative sign here. So we'll say 1, and then we'll say the negative of the square root of sine squared. Now, we know in this case that the square root of sine squared is the absolute value of sine, okay? But in the third quadrant, we know that it's negative. Here, this is already negative because t is in the third quadrant. It's negative because of its definition. But here, this is always non-negative. So we need the negative here based upon this. And now we know what sine squared is. We can write it in terms of cosine squared with the Pythagorean identity. So this equals 1. So we have the negative. And then, of course, remember, cosine squared, I'll just do a little sidebar, plus sine squared equals 1. So we can solve for sine t just by subtracting cosine squared from both sides. So 1 minus cosine squared t. And we're done. So the key here, and this is where I keep going back to arithmetic of the unit circle. When you have to express a trig function in terms of another, and you know where the input terminates on the unit circle, then you must use that to determine the actual sign, plus or minus, of the trig function. And then use the Pythagorean identities, and then, of course, affix the negative if it's needed. Remember, this is a what? This is a positive quantity now made negative. Therefore, in this case, cosecant of t, defined this way, is negative as it needs to be by the hypothesis. So these Pythagorean identities right now seem to be like, okay, interesting. You take the equation of the unit circle and you manipulate it. Okay, big deal, not earth-shattering, but this type of manipulation is essential, especially when you solve trig equations and when you do calculus that involves the trigonometric functions. Now, of course, the only fly in the ointment is that you don't use these every day. There'll be times when you have to use them, and you'll go back and review them. Now, one more thing I want to do, and you'll get practice evaluating values of trig functions. But I want to just do one where we actually compute all the values, and I want to show you something that's interesting now. Now that we have all of these functions, we can just use the sine and the cosine to save ourselves, so to speak. So for instance, if we we're doing WebAssign, and we say, WebAssign says compute the tangent of, say, negative 23, I'll just make one up to make it interesting, negative 23 over 4, negative 23 pi over 4. And you're thinking, okay, well, we're going to have to mod out. We need to mod out because we've got extra stuff here, but we don't have to go through the pain of pushing this into the positive realm. We don't have to do that, because the very first thing we can do is see that tangent is odd. So this negative factors. Tangent is odd, it factors. So this will be the negative of tangent of 23 pi over 4. So this is negative tangent. Now we do the same song and dance. 23 divided by 4. Well, that will be what? That will be 5 with a remainder of 3. So this will be 5 pi plus 3 pi over 4. Okay? So the key here is now we don't have to work as hard, because we've developed some properties of these functions that make our life easier. And now, of course, tangent is pi periodic, so that 5 pi right there is basically a 0. So we've established that. Well, again, we'll say more about it, but now the fact that tangent is pi periodic, that just goes away. So now, using that identity, we have negative tangent of 3 pi over 4. Now, this is the beauty of all of this. At this point, you can say, Professor Ron, I know my unit circle, so I'm not going to worry about the reference number. But notice 3 pi over 4 is in the second quadrant. This is in the second quadrant. So if we want to use the reference number, The reference number is just pi over 4, pi minus 3 pi over 4. But remember, tangent in the second quadrant is what? Y over x sine over cosine, and it's negative. So if we use the reference number, we have to attach a negative. So this will be the negative of tangent of pi over 4. Because here we see t bar is pi over 4. So now we have the negative negative, which is the positive. So we have tangent of pi over 4. And of course, that's just, well, we know that, that's just going to be sine of pi over 4 divided by cosine of pi over 4. And of course, those are both 1 over root 2. So we just get 1. So when you compute these by hand, we don't have to work as hard now, because we can use the fact that now we see that 4 of the basic trig functions are what? Odd: sine, cosecant, tangent, and cotangent. And the other 2, which just leave secant and cosine, are even. So we can either factor the negative or we can absorb it. We can either what? Factor the negative or absorb it. So the important thing here is that we've assimilated some interesting mathematical details about the arithmetic of the unit circle, and we see how they play out. Okay, so when you do integration and you've got trig functions and you're evaluating them using the fundamental theorem of calculus, this will be all over the page. And you'll be like, oh, I don't remember this. Well, that's okay. It'll come back. And this is where this will be very helpful. Okay, so now the last one before we do the graphing a cosine, I want to talk about just a simple computation of computing all of the values of a trig function if we're given enough information to get the ball rolling. So remember, if someone says, is the idea of even and odd important in trig? What's your answer going to be? Certainly. It's like that's one thing we can't do without. We know trig functions are even and odd, and so we have to work with them. Of course, now you see that one of the answers to what I'm going to do is going to be 12 over 13. I promise I won't change it up. Sometimes I just say, okay, well, I'll change it up, but I'll just leave it alone. So here we're going to say compute all values. Sometimes I actually use problems I write out beforehand, but usually, like the last one, the best ones are the ones I just make up, like the trig ones. So compute all trig values, or compute. Let me just write it this way. Let me phrase it a little bit differently. Compute the values of all trig functions. So I'm going to give you enough information to do that. And here's what we're going to have. We're going to have, here's the hypothesis. Tangent of t will be negative 12 over 5. And we're given that sine of t is positive. Okay? This is the hypothesis. So this is the hypothesis. So if we're given this, then we should be able to get the other 5 values. Note, if tangent of t is negative, okay, that's going to tell us 2 things. Either t terminates in the second quadrant where x and y have different signs, or it terminates in the fourth quadrant, again, where x and y have different signs. Okay, so if sine t is positive, that means the y value is positive, so that forces us to be in the what? Second quadrant. So this implies, by hypothesis, that t terminates in the second quadrant. And always use element of, just to be very clear about this. This is my notation, and it's very effective. We need to know where t lives, okay? So again, just using the arithmetic of the unit circle. Now, let's be cheap. Let's start out and do the easy part first. Cotangent is the reciprocal of tangent. So first, just for free, cotangent of t is just 1 over tangent t. So we just flip it. That's just going to be -5 over 12. Okay, so that's a freebie. That was the easy one. It's just the reciprocal of tangent. Now, if we look at this and we think about what we need to do at this point, we can now combine the tangent with the secant with the Pythagorean identity and get secant, and then from secant we can get cosine, and then we're home free. So note 1 plus tangent squared t equals secant squared t. So if and only if secant squared t equals 1, of course, now we'll substitute for tangent, plus -12 over 5 quantity squared. So this gives us 1. Of course, the negative absorbs. So we've got nice numbers here, nice Pythagorean triples. That's always nice. 12 squared is 144 and 5 squared is 25. So we get a common denominator. So we have 25 plus 144. Again, nice numbers. That'll give us a 9 and a 6 and a 1. So 169, of course, that's a perfect square. That's 13 squared. So now, of course, let's just say here, we're in the second quadrant. So that is, we know sine's positive. That means that the x values are negative. So this means we're going to select the negative. So this implies that secant of t, select the negative, will be the negative. You can do plus or minus, but now we can just skip that step. Plus or minus, so now we have the minus square root of 169 over 25, which will be -13 over 5. So we can move the problem forward, and this is where you see these Pythagorean identities are very useful. Okay, and there are many ways to do these problems, ladies and gentlemen, but since we're given the value of tangent and we only have at this point the Pythagorean identities, this is a convenient way to get at the actual secant. So now this implies that cosine, which is the reciprocal of secant, now we just go backwards, will be -5 over 13. Now we've done the hard part. We can just use the simple stuff to get finished. So now we've got everything except sine and cosecant. So we started with tangent, we've got cotangent, we've got secant, we've got cosine, but we observe, if you like, and here's another way to think about this, that sine t is just tangent t times cosine t. Remember, tangent is sine over cosine. So if you multiply by cosine, the cosine's absorbed. So let's just go ahead and use that. So this will say what? Tangent. So we've got -12 over 5. And then cosine is a -5 over 13. But of course, now the negatives absorb, and then the 5s absorb, and that gives us 12 over 13 right there. So what's interesting about this is that, you know, we don't have to go to another Pythagorean identity. You could, but you can just use the fact that sine t and the tangent t are related in such that if we know these two values, we can get sine, just as using the definition of tangent. And now, of course, cosecant is the reciprocal of sine. So this implies that cosecant of t is 1 over sine t, which will now be the reciprocal of this, which is 13 over 12. Okay, so when you think, I mean, computing values of trig functions when you're given the input, not too bad. Just use the properties of the function, mod out, factor the negative or absorb it, If it's pi periodic, multiples of pi are 0. If it's 2 pi periodic, multiples of 2 pi are 0. Then you can use your reference number, or you can go directly to the unit circle. You have plenty of flexibility. However, whatever technique you use, you have to obey the arithmetic of the unit circle. And if you don't, then you have some very interesting answers here. Like a domino effect. Yeah. After finding the corresponding functions, it seems like you are able to find all the others. Exactly. Music to my ears. I like that. That's what we're doing here. We make these definitions and they're all connected. And so what do? We sound like a broken record, even though you all don't know what records are. But when I was little, we played records. And I'm a broken record because every time I say this, I'm basically parroting what I said about the what? Unit circle. So over and over. Now, so now we're just basically getting the basic ideas, just the ground floor, so that we can navigate whatever we're doing right now with the trig functions with some degree of competence. So even though each of the pieces is very simple, when we put it together, we do have to respect the arithmetic of the unit circle. So like I said before, that's all this is. And that's the genius of Dr. Stewart's book by beginning this study this way. Dr. Teague, who I said before, who's written a very excellent treatise on trigonometry, did the same thing. And so I was happy when I came to the North Campus and we elected to use the Stewart text. It's a good book. Now, what we want to do is say a little bit about some basic trig graphs. We're going to start with the cosine. Now, we have what we call a new parent function, and this is easy. So we've got a new parent function. Now, when you think about it, the cosine function as it exists is 2 pi periodic. So what we want to do is, and this is how Professor Ron teaches this, we just look at the input from 0 to 2 pi. And then we go around the unit circle to all the axial terminal points. We figure out those for the new graph, and then we can draw the new graph like we did before using those basic points. Remember, when we would do square root functions, we'd have just enough points to get new points for the transform function, and then we connect them using the shape of the parent function. So when we talk about cosine, let's just write the principal period. It'll go on forever, but that doesn't matter. We just need to, if we understand the shape of one period, then we're done. So at 0, now here's where we get a little bit more flexible. Instead of calling the input t, we'll just go ahead and call it x. And I know you're thinking, oh, don't do that. But I'm sorry, kids, we have to be flexible. So now when we use whatever letter as input, just be flexible. That's what we have to do. Mathematics requires that we are flexible, okay? So when we have an input of 0, we get a 1. So I'll just put a 1 there. When we have an input, I'm going to write off the principal points. Pi over 2, the axial points, pi, 3 pi over 2, and 2 pi. So we just circle back around to 0, so to speak. At pi over 2, cosine is 0. -1. At pi, cosine is -1. At 3 pi over 2, cosine is 0, and then we're back to where we started. So when we draw it, this has a nice smooth shape because it's a differentiable curve. Now, of course, we need calculus to prove all of this, but we don't have calculus yet. So we have to assume that Professor Ron is giving you a graph that's reasonable. So the cosine function it looks like a polynomial, but now as we keep going this way, it repeats, and you keep going that way, it just repeats. This is the principal period, 0 to 2 pi. And so if we transform it, we might compress it, we might stretch it, we might shift it, right or left, up or down, and we may stretch it or compress it vertically, just like we've done all the other functions. So the key here is, how do we do it? Well, how have I taught you to do it? I've taught you the way to do it. However you did it before is of no consequence to me. How I've taught you to do it, especially as we reviewed, will now be the same structure that we do for this. What we want to do is just move these simple points with our transformation, plot the new points, and sketch the graph with this shape. Now, of course, the concavity, the shape of all of this, decreasing, increasing, you're going to get that in calculus, but the calculus is going to verify what we have here. So this is our new parent function. Parent function. Of course, computers give you beautiful graphs because they plot 5 million points or 500 points and, you know, whatever. But again, we know that the graph looks this way because we understand it. And when you get to calculus, you'll be able to verify all of this. So what we want to do is look at the basic graph. So the basic graph of the cosine will be A cosine K X minus B. So you're looking at this and thinking, okay, those are the kinds of letters we used before, but a little variation. So what we're going to do is we're going to fix K to be a positive number. That'll be a fixed positive number. So just remember, if we had a negative there, if it were a sine or a cosine, it could either be factored or absorbed. So we will insist that K is positive. And if it's not, get rid of it. If it's a cosine, it absorbs. If it's a sine, it factors. So you don't have to deal with that anymore. It's not going to be a problem anymore. A, again, that's going to be a vertical stretching or whatever, depending on compression. And then, of course, this will be a shift right or left. So what we're going to do is say that the absolute value of A will be the amplitude, because again, these functions live between -1 and 1. So this amplitude makes sense. Of course, for cotangent and tangent that go off to infinity, amplitude doesn't make any sense. So we won't talk about that for those functions. And then the period, we're talking about a horizontal stretching or compression will now be the basic period divided by K. So of course, if K is between 0 and 1, then this gets bigger. If K is bigger than 1, this gets smaller. So this is exactly what we did before, but now we say the new period is 2 pi over K. Remember cosine, we say Y equals cosine X is 2 pi periodic. And then the last thing is the phase shift. This is the terminology we use for the right or left shifting, and this will be B. And of course, if B is positive, this corresponds to a right shift. And if B is negative, this corresponds to a left shift. So again, if B is negative, we get X plus B. If B is positive, we get X minus B. So this is exactly what we did before. But the actual phase shift, it carries the sign in a way that we haven't done before. So again, this is still the same construct that we did in the college algebra review. It's just now the terminology for phase shift incorporates signs. So again, with the positive B, this is exactly what a shift to the right by B. When we have the negative, we get the plus here because the negatives absorb, and then we get a shift to the left by B. So that's the same thing we've done before. So the idea is that we take these points and shift them. So here's an example. We'll say Y equals 5 cosine of 3x. I just pulled this right out of the book. I opened up the ebook and I thought, oh, this is a perfect example. This is just like your WebAssign. But of course, they don't teach it the way I do. I mean, I don't really understand it. because, you know, you'll look at the graph and say, where did those numbers come from? I'm going to show you where you get the numbers. So now we want to make this look like this. So we need to factor the 3 so we can figure out what the K is. So here we just want to graph 1 period. It often will say just graph. It'll often just say just graph. And so all you need to do is 1 period, because after that you can extend it infinitely, but we can't do that. So we just do 1 period. So this will be 5 cosine 3, factor the 3, and of course we'll need to divide by 3 here, so this will be minus a pi over 12. So again, 3 over 3, the 3 times the 4 gives us the 12, and then we pull out the 3's and we've got this. So now we can see that we have an amplitude of 5, we have a phase shift of pi over 12, and we have, well, we can write it down, so we can say amplitude is 5. And now we have phase shift B. This is pi over 12, and I'll just write it to right. Again, we know it's to the right because it's positive by this convention here. And then, of course, the period now, which we'll see from our transformation, would just be 2 pi divided by 3. So it's what? It's smaller. And so now we will have the period that will run in this particular case from pi over 12 to 2 pi over 3 plus pi over 12. So again, the graph is going to be stretched, but it's going to be shifted over pi over 12, but then compressed. So in order to get the points, we need to move the easy points and not guess. So let's do it. And I'll get common denominators to show you how, if you get your common denominators as you work through, you don't have to guess at the points. So we'll have, just go ahead and write them down, 0, 1, pi over 2, 0, pi, -1. If you look at my Smart Pen videos, these are kind of what I do. The first time I did the online course, I taught it this way because I taught it this way at Texas A&M. Well, when I did the calculus TA, but mainly when I started teaching at San Jac, I adopted this because I thought it made the most sense. So now let's just see what this is. We've got cosine. And then we go here, we do a what? In this particular case, we'll do a horizontal compression by 3. So H compression by 3. So that gives us cosine of 3x. And now we can do right shift by pi over 12. Right shift pi over 12. So x minus pi over 12. Use the brackets to make it a little clearer. And then we do a V stretch by 5. V stretch by 5. And that gives us 5 cosine 3 x minus pi over 12. Okay, so now we just want to move the points. So we'll just shift this down a little bit. So now we do an H compression. So all of the x coordinates get divided by 3. So we have 0 over 1. And then we get pi, in this case, pi over 6. And then we get pi over 3. And then we get 3 pi over 6. Just leave it alone. 3 pi, don't absorb anything. It'll be easier to get a common denominator. And then 2 pi over 3. So now you see that's actually the new period here. We see from this calculation, the distance here is just 2 pi over 3. So this is consistent with this calculation here. So now we need to do a right shift by pi over 12. So let's just go ahead and get common denominators. So we have 0, 1, and then we have 12, 2 pi. Just get a common denominator so it's easy to do the common, do the shift. And then of course here we need a 4. So we'll do 12, 4 pi. In here, we need a 2. So we've got 12. So that gives us a 6 pi. And here we need a 4, right? So that'll be a 12, and that'll give us an 8 pi. So this is a little side calculation so that when you do the shift here, you've got the correct denominators. Just a little added detail that I've started incorporating to make the arithmetic easier. No need to struggle. And so now right shift by pi over 12. So we get pi over 12, 1. Then we get what? 1 plus 2. So 3 pi over 12, 0. 4 plus 1, real hard, right? 5 over pi, 12, negative 1. Then we get a 7, right? 6 plus 1, 0. And then what? 8 plus 1 is 9. Don't reduce. Because now you've got these points that you can plot on the x-axis that give you the points that you see in the book, and no one tells you where they come from. See, that's the issue with doing mathematics the way I teach it. You have to figure out what the new points are, and you can't do it by using a fancy calculator. Again, you know, you might as well take your fancy calculator and put it somewhere where you can't get to it, because it's not going to do you any good, at least not in my class. So now you can see that the basic arithmetic gives you the blueprint. And then now we'll do the easy part. We'll just multiply all of the y coordinates by 5, and we got our new points, which we can plot, and we're done. So now, pi over 12, 5, 3 pi over 12, 0, 5 pi over 12, negative 5. Technology is terrific. It's why we can do Zoom, but reliance upon it will ruin your ability to do mathematics. So now all of these new points basically give us the new graph. So we've taken the easy points here. Now you might be thinking, do I have to do all of these points? Well, here's the thing. Here's the thing. We've kind of got the max, the min, and the intercepts. So if you're doing a really simple curve that you can kind of just intuit in your brain, you may not need to do this. But when you have shifts here, when you're compressing the period and you're shifting, the points are really important. And for instance, I might just say, provide the 5 principal points on the test. You'll do the graph, but I may just say, okay, here's a function, shift the principal points and provide the new points. And if you have the new points, you're done. So now we can take this, just do a real simple graph. We'll just do like in pencil here, and be judicious with our scale. So we just need one period. So now notice we can go ahead and mark off, if you like, a 5 and a negative 5. 5, negative 5. And now just go ahead and put in the x values, all with the same denominator. So we'll do a little flexibility here. Pi over 12. So that'll be 2, and then we have 3 pi over 12. There's 4, and now 5. There's 6, and now 7. There's 8, and then 9. So now what you see here is that when we subtract pi over 12 from here, we just get 2 pi over 3. So everything is consistent with our calculations. Maybe WebAssign just says, okay, just give me the amplitude and the phase shift. Maybe that's all they ask of you. And then, of course, if you've got to plot it, you've got to do all of that anyway. So this kind of puts all the ideas right out front. So nothing I've done here is new. It's all old. We just have a new parent function. Like when you did the logs and the exponential curves, that was simple. Those are simpler than the square root functions. But the thing is that the same techniques are in tow, and we simply move the simple points on the curve. And then we can plot them. So now you can take another color pen. So pi over 12, 5 would just right there, and then the 0, and then the 5 pi over 12 negative 5. Again, this is not Rembrandt, it's just a reasonable depiction. 7 pi over 12, 0, and then 9 pi over 12, 5. And so now we can just connect this, again, using the shape here. We didn't invert anything, so now we'll just go ahead and fill it in. And here's one complete period. And then, of course, once you've got the complete period, especially if you're doing the WebAssign, you can look at the axes and say, oh, yeah, this is right. You've got the points here. So once you've determined these points, you basically understand the new curve. Okay. So you might be thinking you could do an upward shift. For instance, we could add 2 to this and shift all of these points up by 2. Okay. But what you're seeing here is that the standard function here may be simpler, or maybe just an additional, say, like an upward or downward shift that you would tack on here. So again, just remember that all of this terminology is based on what we've done before. There's absolutely no difference, absolutely no difference. The terminology now is that we have the period, and then the great minds got together, and I think this was more based on physics and engineering. They term the shift phase shift, phase shift, and that has to do with harmonic motion and how that terminology is set up when you talk about springs in differential equations. We'll do springs with Hooke's law with work calculations in calculus 2, but when you get to differential equations, you're going to solve second order homogeneous and non-homogeneous equations that deal with harmonic motion, and that is central to the study of kinematics. Physics and differential equations, that was a marriage made in heaven, basically because Newton and all of his contemporaries discovered the connection. And so when you try to describe motion and you describe our world, the language of calculus is just what it is. And we see that the more we study, the more we're made aware of the fact that we can't divorce ourselves from calculus. It's just part of our world. I mean, numbers are part of our world. It's why we have this great technology. And so again, STEM puts you right in the middle of it. So now, as you work your WebAssign with the sines and the cosines, of course, with the sine, we would just flip the points around and you do the same aspect. So for now, when you're trying to graph a function, just move the simple points and then you will be fine. So with the sine function, let me just go ahead and give you those so you can do that with your WebAssign. So with the sine, remember, it starts out, just use your unit circle. It starts out at 0, 0. Then we, of course, have pi over 2, pi. We have 3 pi over 2 and 2 pi. So this is the sine function, y equal sine x. And so now you can mark off your 1 and your -1, just be, generous here. So now at pi over 2, we're 1, and at pi, we're 0, of course, multiples of pi, and then at 3 pi over 2, -1. And then, so here is our principal curve, or our parent function for the sine function. So now, just like the cosine function, when you want to graph a sine function, ladies and gentlemen, all you have to do is move the principal points. And so the principal points here will be 0, 0, pi over 2, 1. This is just the unit circle, right? Pi, 0, 3 pi over 2, negative 1, and then back around to 2 pi comma 0. So these again give you the highs and the lows. And so if you plot these points under the transformations, then you've got a nice set of points that you can easily connect. So just like we would take 0, 0, 1, 1, and 4, 2 for the square root function, we just add a couple more here. And I found that if you move these points, just like we have here, well, I put it under here, you always have just enough points to get a nice, reasonable picture. So now when you do the sine function, again, it'll be y equals a sine, and then you do the same thing, k x minus b. It's the same thing, same definitions. So as you work through these, you're going to see some that are just really easy. And so, oh, they just stretch this. I mean, that's so easy. I can do that in my head. Of course you can. But what I want to focus on now is that I want us to use the techniques we've already established in college algebra now to apply the trig functions. And so, of course, again, let me just repeat, no trig on this test. On Thursday, I'll just do some review problems like I've done in the past for the test. And that'll just mean, doing problems from, the sections that we've already covered, just to give you some additional reinforcement. Some of you may already be ready. You're like, I'm done. I know this stuff. I'm ready to take the test. But I've decided that having an opportunity just to do some more review is good, just to kind of get your mind moving with all of that. But again, do not worry about trig for this test. There will be no trig on this test. And of course, I'll have my same office hours, and then on Thursday, the Blackboard test with the Turnitin will be available. Remember, and I've talked to a lot of you all about this, I use the Adobe Scan. A lot of you use other methods or whatever, but I want the nice, clean scans of your work in one file with Turnitin app, just like we did for the last one. I'm not going to accept any email versions, okay? We're college students. You know what I'm asking of you. I want to have your test work and your Blackboard test in the same place so I can assess them. That is just a matter of following rules. And I appreciate the fact that you all do that. But again, remember, the Adobe Scan that Professor Ron uses is really useful. And you can use that in all of your classes. I mean, I'm sure you have to turn in work, for science, for English or whatever. The Adobe Scan app is exceptional. It is an exceptional tool. And it's something you can use in all aspects of your life. You might be working on a problem with a colleague in your class, and it's like, oh, let me just scan this and send this to so-and-so and they can see what I've done or whatever. It's a wonderful, wonderful piece of software. And of course, there are other free apps at the Google store or the iPhone store that you can use. So make sure that you step it up and give me a nice rendering of your work. And those of you that told me what you were going to do, I was very impressed that you took the time to think about it. I appreciate that. And of course, remember, your work supports the answers that you choose. An unsupported answer is a wrong answer. So I need to see the support, and I do not want to see homework site solutions. If I see that, and I saw it on the last test, I will put a 0 on your paper. I will not tolerate that. Ladies and gentlemen, integrity in your work is essential. And I've said that over and over, and it seems to be something that no one thinks about anymore. But I encourage you to go to the Blackboard site and read the philosophy of San Jacinto College when it comes to the academic process. I say that's why I believe in San Jacinto College, and that's why a degree that you receive from this school will be legitimate. It will be something that can push you into the next phase of your life at the university, okay? So now that all the hard stuff has come out and we know where we stand, I will send out invitations for the conference hours today. Good luck as you study. If you have WebAssign questions or whatever, just send those messages and I'll get right back to you. Again, thanks for your attendance today. Enjoy the nice weather and let's keep our fingers crossed that it actually lasts. No weeks of rain. I want you all to have a spring break that's really nice. But have a great day and we'll see you soon.